Thank you very much for kind introduction. My name is Tomoo Nakai, and I'm a research staff of Japanese local government, Miyagi Prefecture, which is located in Japan. I'm belonging in research technology in Miyagi Prefecture government, and this is a technical support institute for local enterprises. Today's my talk is concerning about magnetic domain observation of stepped giant magnetoimpedance sensor with subjecting to normal magnetic field. This is the outline of my presentation. My talk is concerning about domain transition for thin film giant magnetoimpedance sensor. So I'd like to firstly introduce the thin film giant magnetoimpedance sensor. The sensor is a rectangular shaped thin film element in which a high frequency current is induced and the element impedance changes as a function of external magnetic field. My element is made by soft magnetic amorphous magnetic thin film. And magnetic anisotropy was induced in the in-plane direction by using magnetic field annealing. The direction of uniaxial EJ axis was controlled by the direction of magnetic field while annealing. A high frequency current is induced along the length direction. The sensing direction of this element is the length direction because of a very thin film and narrow width and long length with its shape. When the external field is applied, when the external field is zero, the magnetic momentum in the element is forced by magnetic anisotropy. Therefore, it orients in the direction of EZ axis and make a certain domain structure. And as increasing the external field, the domain structure changes and the magnetic momentum rotation occurs. This figure shows the variation of impedance as a function of external field. It's a well-known MI curve. The element is made by amorphous cobalt niobium zirconium and the thickness 2.2 mic and the width 20 mic and the length 2000 micrometer. The lower picture shows the magnetic domain image. When the external field is zero, the impedance is the minimum value, and the magnetic domain has an inclined Landau-Lifshitz-like domain. In this case, the EZ-axis direction is matched with the domain of direction. As increasing the external field, the width of domain changes and also magnetization rotation occurs, and simultaneously the impedance changes. This is an example of linear property of impedance variation. I'd like to show the stepped property of this element. The stepped GMI property occurs simultaneously with the change of magnetic domain. This figure shows the variation of impedance as a function of external field. There is disconnection of impedance. When the impedance is larger value, the domains are single domain with positive direction or single domain with negative direction. And lower impedance, when the lower impedance state, the domain state is multi-domain. This property is obtained by controlling the EZ-axis direction. It is obtained when the EZ-axis direction is ranging from 60 degrees to 70 degrees relative to the short side axis. And this property has hysteresis when increasing external field and decreasing external field. For easy to understand this phenomenon, a state diagram of magnetization is usable. This figure shows the variation of magnetization for the element as a function of external field. The external field is applied along the in-plane length direction of the element. It's a measurement direction. And in this sheet, there is a domain image is also shown. The upper state represents a single domain with positive direction, and the lower state represents a single domain with negative direction. The middle state represents a matched domain state, and as changing the external field, the domain width changes. The domain transition from single domain to matched domain occurs when the endpoint of these domain states. This is an example of variation of domain state. For these figures shows a different variation range of external field. We can see that when the domain state changes to multi-domain state, the middle state, it kept within the state between its endpoint. And this is impedance variation for the same element. We can see compared with the previous state, the multi-domain state has lower impedance. And based on our previous study, the property of magnetization is controllable by controlling easy axis direction. When we control the theta to more large value, to red axis, red arrow, the endpoint of the single domain state extend toward the red arrow direction. If we control the property like this, the element magnetization property is limited between two states, between single domain with positive direction and single domain with negative direction. Based on our numerical simulation, there exists a multi-domain state, and the magnetic energy of this state is lower, and it's a stable state. In this case, the matched domain wouldn't appear even if we control the external field in any value, but it's a stable state. So physical fundamental interest appears how to reconstruct this stable state from single domain state. This is the aim of this study. And if it would be realized, it's possible to applicable for memory device or sensor with memory function. I'd like to introduce my previous study, which is a trial of application of normal field to the element. It's reported to summer 2013 and published in this paper. And in this study, a normal field is applied by C-shaped core to the element. As a result of this study, this is the variation of impedance as a function of external field for the element which has an easy axis in the direction of 60 degrees relative to the short side axis. This is impedance variation as a function of external field when the normal field would not apply. This is the typical impedance variation for the stepped GMI element. The lower impedance state is a multi-domain state. And when applying normal field and increases 9.2 kiloampere per meter and 30.0 kiloampere per meter, the lower impedance range widens as increasing the normal field. So it is expected that the multi-domain state range of multi-domain state widens as increase in the normal field. So I assume that this method is applicable for reconstruct the multi-domain, reconstruct the hidden stable state. From here, a new result. In this report, an observation of magnetic domain was carried out with subjecting to normal field. Observed by Kerr-microscope, and we made apparatus for applying normal field on substrate. And as a result of the study, two results are obtained. One is appearance of multi-domain by applying normal field is confirmed. And second, it's important result, the controlling parameter is a distributed X field parameter, dBx/dx. I'd like to explain more detail about the distributed parameter. This figure shows the schematics of the field, of the normal field with distributed X field. The Z direction is a normal field of the element surface, and X direction is element longitudinal in plane direction. The field with distributed X field consists of constant BZ normal field throughout the sensor element, and also the distributed X directional field, which has a function as a function of the X point. In this study, the Bx field has a linear function. Therefore, we define a distributed parameter dBx/dx as a constant value. I'd like to show my experimental apparatus. This is a Kerr-microscope. We observe the magnetic domain structure by using this apparatus, and it's using Kerr effect. And applied normal field and with distributed parameter is controlled by two ring magnets. The strength of normal field is controlled by the distance of two ring magnets, and the distributed parameter is controlled by the place, the directional place of a magnet unit. This is a consolidated one. This is the link coil magnet unit, and which is moved by XY space and also gonio space. It compensates the Z directional angle. And this is mounted on Kerr-microscope. And I'd like to show the magnetic field variation in the measurement area. It's measured by whole magnetometer. This figure shows the variation of magnetic field as a function of on different plane in the measurement area. The number one plane is the one just middle position of this magnet. The range is X 4 millimeter and Y 4 millimeter. My element is 2 millimeter length. On the plane 1, just middle position, the normal field is 125 Gauss. And this variation of the X directional field, Bx, is flat plane. Therefore, the distributed parameter dBx/dx is 0. On the just middle plane, the normal field is just parallel to the normal field direction. And as increasing Z position, the normal field is almost the same, but slightly decreases. On the other hand, the variation of X directional field changes like this. The distributed parameter dBx/dx increases, and this variation shows a flat plane canted towards the X direction. Therefore, in the measurement area, the dx/dx is a constant value. The normal field is controlled by the distance of the magnet. In this case, the value is almost twice the previous one, 280 Gauss. Okay, I'd like to show the experimental result. This figure shows the experimental conditions that I carried out. The vertical axis represents a normal field value, which is ranging from 100 Gauss, 300 Gauss, and 600 Gauss. And the vertical axis represents distributed parameter, which is ranging from 0 to 5 Gauss per millimeter. We carried out three conditions of a normal field. And I'd like to show the case when the normal field is 270 Gauss. This sheet shows the variation of magnetic domain as a function of a longitudinal field. We carried out this measurement by applying normal field with distributed field, static normal field with a distributed field to the element, and controlling the uniform longitudinal inclined field in the x direction. The lateral scale represents the value of applied field in the inclined direction. The upper figures represent the magnetic domain when increasing external field, and the lower figures represent when decreasing external field. This is a image of Kerr-microscope, and estimated magnetization direction is shown by arrow. This strip chart shows the domain pattern. The dark area represents single domain with negative direction, and white area represents single domain with positive direction. This measurement was carried out for the element of z-axis in the direction of 71 degrees. In this condition, the element has a hidden stable state. And this sheet was carried out without application of normal magnetic field. When increasing external field, the domain transition from negative to positive occurs at about 0.65 Gauss, and when decreasing external field, the magnetization transition occurs at minus 0.62 Gauss. This is the estimated MI curve. It has a hidden stable state. And when applying normal field, 280 Gauss, and the distributed parameter is zero, just parallel normal field is applied. In this case, the domain transition is the same as the previous one. It's limited between single domain with positive and negative. So, in spite of application of normal field, the MH loop is remains, which has a hidden stable state. This is a case when the distributed parameter is 2.7 Gauss per millimeter, and the normal field is almost the same as the previous sheet. We can see multi-domain state appears in a certain range of applied external field. This is the estimated energy curve, and multi-domain state appears out of hidden state by controlling the distributed parameter. As increasing the distributed parameter 5.0 Gauss per millimeter with keeping the normal field, the range of multi-domain widens. In this case, the multi-domain appears even if the external field is zero when increasing, both when increasing and when decreasing external field. This is, we carried out other two conditions of a normal field. One is, normal field is 120 Gus, and the result is the same as the previous one. When the distributive parameter is 0, the domain transition is limited between single domain and positive and negative. And it's with a hidden stable state. And as increasing the normal distributive field with keeping the normal field, the range, the matched domain state appears and it widens as increasing the distributed parameter. Now, for the case of normal field 640 Gus, it's the same as the previous one. It's dBdx is 0, and as increasing the dBdx, it appears and widens. And in this case of normal field is 640 Gus. Sometimes an extraordinary domain was observed. It's like a bubble domain, and the details is not clear now, but there is some phase transition of magnetic domain appears by controlling the normal field value. I'd like to summarize my presentation. This is a summary of the experimental results. Estimated MH curve is plotted on the measurement condition. Please notice when the distributed parameter is 0, the MH curve is the one which has hidden stable state in spite of the normal field value. But when controlling the distributed parameter, the matched domain state appears and as it widens as increasing the distributed parameter. Okay, and I'd like to introduce magnetic simulation about this phenomenon. This is a collaboration with Professor Matsuo, Kyoto University, and his method of assembled domain structure model is applied to my element. This simulation model is suitable for mesoscopic large scale micrometer to 1,000 micrometer scale domain structure. And his simulation successfully explain my experimental result. Based on his simulation, the only parallel normal field would not change the MH curve for the case of the element with hidden stable state. But when applying the distributed parameter in the direction of in-plane length direction of the element, the magnetization curve changes and the matched domain state appears. Okay, I'd like to conclude my presentation. This is Acknowledgement. Thank you very much for your attention.